Let me begin by expressing thanks to the organisers for this invitation. It's a great pleasure to speak about our recent work on machine learning and nonlinear fibre optics. This work has been carried out in collaboration with a number of students and researchers from my own institute, as well as from Tampere in Finland and Dijon in France. It's well known, of course, that the tools of artificial intelligence have tremendous potential to change how we do research in photonics, and there's currently extensive work being carried out worldwide developing different aspects of the field. A number of review articles have recently appeared highlighting many recent areas of progress, but it's important to remember that the initial ideas of machine learning and optics date back to the 1980s. What's making it feasible today is the availability of technology. We published a review last year focusing on particular applications in ultrafast photonics. And if you're unfamiliar with this particular area, the review provides a summary of the main areas of application, from technologies such as laser optimization and control, to very exploratory topics such as model discovery from analysis of data. In this talk, I want to focus on a very small subset of this. Specifically, I want to address how both experimental and theoretical studies in ultrafast nonlinear propagation in fibre can benefit from some specific machine learning methodologies. Before talking about specific aspects of machine learning, though, it's worthwhile discussing briefly the overall context. In the case of nonlinear fibre optics, probably the key result in the last 15 years has been the use of real-time measurement techniques to analyze nonlinear propagation phenomena. And it's this, the availability of real-time measurements, that has really opened up the need for new approaches to data analysis. One key paper here was the celebrated 2007 Rogue Wave paper by Jalali and Solly et al., which showed the power of statistical analysis of supercontinuum instabilities to establish links with other areas of physics, specifically the formation of giant rogue waves on the surface of the ocean. Although these experiments were performed in optics, the results opened up a host of new interdisciplinary connections with other fields of physics. If you're interested, our 2019 paper discusses the optics ocean correspondence in detail, with a complete discussion of how the analogy works, all the necessary transformations between the different equations, typical results, the key vocabulary that's used in the two domains, and many, many references. In the optical domain, though, we're very lucky now to have real-time techniques, as I mentioned before, for both spectral and temporal measurements. It was the dispersive Fourier transform that opened up the field of optical rogue waves, and this is shown on the left. It's based on the fact that the dispersed temporal profile of a pulse in an optical fibre will asymptotically evolve into a scaled replica of its spectrum for sufficiently large dispersion. The time lens technique, which is shown on the right, is based on applying a temporal quadratic phase to an incident picosecond pulse to essentially emulate the effect of a thin lens magnifying a picosecond or sub-picosecond signal to nanosecond duration, where it can be directly measured with a fast gigahertz oscilloscope. Both of these techniques have been used either separately or together to study a range of nonlinear propagation phenomena. A particular experiment that we performed a few years ago was the application of a time lens system to directly measure the peak intensity fluctuations in ultrafast modulation instability. Modulation instability, or MI, is the fundamental process in nonlinear fibre optics with anomalous dispersion, amplifying quantum noise to macroscopic levels and leading to incoherent turbulence, and other manifestations of unstable propagation. Although these time lens results were fantastic to obtain, the difficulty is the time lens setups are very complex and are not always possible at all wavelengths. So this motivated, in fact, our first attempt to use machine learning. In particular, we asked the question, if we can use the simpler technique of real-time spectral measurements using the dispersive Fourier transform or some other method, for example, can we use machine learning to still infer some information about the temporal behavior? So these plots, for example, show the kind of thing we're talking about. We see both the spectral evolution over a bit more than 3.5 meters in fibre on the left, with the corresponding temporal evolution on the right. And at the output, we show line plots of the spectrum, which has this long triangular shape, and the corresponding intensity. The question that we're asking is whether, based on this spectral information only, is it possible to determine, for example, the peak of this intensity profile on the right? This slide shows the particular experiment that we would wish to analyze. We inject short pulses into a laser and we generate shot-to-shot variable spectra. In the time domain, these spectra are associated with variable temporal profiles, and the idea is to ask ourselves whether a neural network can be used to map these spectra to these peak intensities on the shot-to-shot basis. Can we train a neural network to recognize the inherent patterns in the spectra and to output predictions for the peak temporal intensities? So the idea here is that we use a standard feed-forward neural network architecture with 2 hidden layers, and we use numerical simulation data to correlate the full modulation instability spectrum, which is input to the input layer, with an output corresponding to the peak of the associated temporal intensity profiles. We train using 30,000 simulations over 300 epochs. After training, we tested the network using 20,000 simulations which were not used in the training phase, and we found indeed that we were able to successfully predict temporal peak intensities based only on the spectral data. It's important to stress here that we're inputting spectral intensity. So there's no spectral phase information being input to the network. And yet we're still able to successfully predict temporal peak intensity with a correlation coefficient of about 0.92. This is very good news, but the training also shows that to be successful, we can't really use real-time measurements such as DFT yet because they don't possess sufficient dynamic range. The simulation and the training seems to suggest that we need over 50 dBs of dynamic range, which requires that we built a specific real-time scanning bulk monochromator for the real-time spectral characterization. So that in the setup shown on the left, the false color plot in the middle shows 60 typical spectral measurements made with the setup. We can see 2 of them with especially large bandwidth. And on the right, we show 2 typical examples of a broadband and narrowband single shot spectra in red compared to the mean spectra to indicate the degree of fluctuation that's observed. Once we have our measured spectra, we input these to our network, which was trained on simulation data, in order to try to predict the expected temporal intensity distribution based only on the spectral information. The curve on the right shows the summary results of this process, where we plot the probability distribution of the temporal peaks obtained from the network predictions from experimental spectral data, and we compare this with the expected probability distribution from simulations of the entire system. There's excellent agreement between the two curves that are shown. The curve on the left, for completeness, shows the form of the spectra obtained, comparing the real-time spectrometer, which is the dashed line, a measurement from a classic averaging OSA, and the simulations, which is the blue line. Note that we really do need this high dynamic range setup. The 20 or 25 dB or so from a typical DFT, which is shown in the inset, is not sufficient to perform this neural network prediction. A more complex class of instability in nonlinear fiber optics comes from lasers, and specifically the noise-like pulse laser that emits a highly complex multi-scale sequence of pulses where 10 to 100 picosecond envelopes modulate random picosecond or sub-picosecond solitons. Typical spectral and temporal evolution maps in such a system, shown on the left over one round trip, are shown in the two false color plots. And the question is whether we can similarly predict the temporal behavior of such a system based only on spectral data. An additional element of complexity is that this class of laser operates in many different regimes depending on the length of highly nonlinear fiber inserted in the cavity, from narrow band spectra, which have a form similar to those seen in modulation instability, to broadband spectra, where the intracavity dynamics involve supercontinuum processes such as discrete Raman soliton formation and associated dispersive wave emission on the short wavelength edge. We can see in this case that the spectra span over 700 nanometers at the minus 20 or 30 dB level, and the corresponding time domain structure is extremely complex. The plots in the bottom show 5 typical simulation results, and again what we're going to try to do is ask the question if we can train the network to learn the patterns from the spectra on the left to predict the peak intensities of the complex profiles on the right. Although this may seem a daunting challenge, it works. Although I have to stress that we've only tested this on simulation results at this stage, the experiments are much harder. Trying to get a spectrometer system working with 50 or more dB of dynamic range over a large bandwidth is extremely challenging. However, the results on the left show correlation plots in the narrowband regime with excellent correlation coefficients of greater than 0.96. The left-hand subplot shows the results over the full dynamic range of simulation data. The plot on the right shows the results with 50 dB of dynamic range, truncated to reflect what might be possible in an experiment. For the broadband laser operation, even with the full dynamic range, the correlation is lower, as might be expected based on the complexity. And it seems that to obtain any kind of reasonable correlation, we need at least 80 dB dynamic range over this broadband. That probably isn't attainable at the moment, although there are new techniques emerging which might make it feasible in the near future. A related problem to that of intracavity supercontinuum generation is actually to use a neural network to go back to the original 2007 rogue wave supercontinuum experiments and try to gain some additional insight. In particular, we know from both experiment and simulation shown here that supercontinuous spectra at the output of a fibre show large shot-to-shot fluctuations, and in particular the appearance of a more or less distinct redshifted rogue soliton pulse. The dynamics that lead to rogue soliton generation are shown in these two false colour spectral and temporal plots, where when one performs a large ensemble simulating supercontinuum generation with a generalized nonlinear Schrödinger equation, then most of the simulations, over 99%, will look like those on the left, with moderate spectral broadening and a reasonable clustering of the temporal soliton pulses that are associated with that. A very small number of rogue events will look like those on the right, where we see a clear and distinct separation of a rogue soliton pulse in the wavelength domain and the equivalent separation of a high peak power temporal soliton pulse in the time domain. The physics of this is associated with inelastic collisions that allow energy transfer. It's quite well known now in the supercontinuum literature, and so I won't talk about this. The key point that we're trying to ask is whether we can train a neural network to predict the properties of the rogue soliton pulses based only on the spectra. So this is what we're trying to do. The figure on the left shows how we would like to start with spectral measurements and predict properties of the rogue soliton pulses, such as its temporal peak power, its duration, and its walk-off from the central pulse. Just to explain a bit more what the rogue solitons correspond to, the simulation results on the right show 5 different supercontinuous spectra with different levels of separation between the soliton pulses and the rest of the spectrum. In the frequency domain, the Fourier transform of the blue shaded component is the time domain blue pulses that you see on the right. However, we've found that it's necessary to train a network not just on the long wavelength filtered component, but on the entire supercontinuum spectrum, as shown in the schematic of the neural network here. Again, it's a standard neural network architecture, and we train using 20,000 simulations to correlate the supercontinuous spectra with the peak power or intensity of the rogue soliton in the time domain. Once the network is trained, we test using 10,000 simulations, an additional 10,000 simulations not used in training. Based on the network results, we then plot the predicted intensity, which is on the vertical axis, against the known intensity from the simulations in a scatter plot, and once again we obtain very, very good correlation. In fact, in addition to predicting just the soliton peak power, we also succeed in training the network to predict the soliton position, its temporal walk-off relative to the center of gravity of the pump, and with a albeit slightly poorer correlation, the soliton temporal width. Now, significantly, although these correlations may appear to possess significant scatter, one cannot predict them at all from simpler metrics associated with the supercontinuum field. These two plots, for example, which we can see immediately show essentially no correlation at all, attempt to predict the soliton peak power from the spectral width of the supercontinuum at the minus 30 dB level, that's the plot on the left, or the energy contained at long wavelengths in the filtered component of the spectrum, and that is the plot on the right. Now, this clearly doesn't work, and this highlights the remarkable power of a neural network to find connections between quantities where we may not think, based on our intuition, that such connections readily exist. In fact, neural networks can do a lot more than correlate MI or supercontinuous spectra with a particular temporal output property. In this work, we've shown that they can be used to essentially replace direct integration of a generalized nonlinear Schrödinger equation in a numerical simulation via a direct neural network emulation. This is a bit more involved, but the essential idea is to use a recurrent neural network to compute a profile of a spectrum or an intensity or temporal intensity at some distance from 10 previous spectral or temporal profiles. This process then iterates along the length, allowing you to start with some input and sequentially to generate every intermediate step in the evolution as well as the output after a specified distance. This slide shows the results obtained. Here we use a training set of 1,000 simulations with the Fibre and pulse parameters as shown, and we scan the peak power over 500 watts to 2 kilowatts so that we see a range of qualitatively different evolution maps in the simulations. These are then used to train a recurrent neural network, and then we test it using some other particular value of input power, which was not explicitly in the training set. And the results are shown on the bottom, where on the left we compare the generalized nonlinear Schrödinger equation and recurrent neural network temporal intensity maps, and we can see that visually they agree remarkably well, and the subplots on the right overlap the intensity profiles at a particular distance, and the agreement is remarkable. And similarly, there's very good agreement in the spectral characteristics, which are shown on the right. Interestingly, although recurrent neural networks are probably the most natural system adapted for this class of problem, even a feed-forward network can also perform this replacement of direct integration. Here the idea is similar, but the training data is simply pairs of input intensity in the time domain and spectral domain over a small integration distance. So the network learns how to model differential propagation. We input this data over a wide range, and then to model one particular propagation scenario, we would inject an input to the network, and then we would iterate. The results shown in the bottom for the spectral characteristics, comparing the nonlinear Schrödinger equation on the left and the feed-forward neural network on the right, they're again visually indistinguishable on the scale, and when you compare in more detail the profiles on the right at the selected differences, the agreement is also very, very good. These results have just been published in Optics Letters. Finally, I'd just like to spend some time on some very recent results. They've just been published a week ago, in fact, where we use a technique known as sparse regression to analyze data from a nonlinear optical system and to reverse engineer it to determine the underlying differential equation model that describes the system. Now, this is a remarkable development in machine learning. It's been developed since 2016 by Brunton, Proctor and Kutz in this paper in the Proceedings of the National Academy of Sciences. And the technique is generally known as sparse identification of nonlinear dynamics, or SINDI. Now, ultimately, the idea here is to analyze data from some unknown system and to use the regression approach to determine a new and unknown physical model to complement other ways we use our intuition or experience or guesswork to describe some experimental data and to identify the underlying physics. Now, what we're doing at the moment is we're testing the applicability and the limits of this technique on specific systems in nonlinear optics, where we have a priori knowledge of the model. So what I'm about to describe may seem a little bit strange because we know what the answer is to start with. And so it may be unclear why we'd use this technique, but the point is to test this approach, which is really extremely new. And these are the first results shown on a four-wave mixing system, for example, to demonstrate its feasibility. The technique itself is quite involved, but the software and the algorithm involved is freely available through open source by looking at the Brunton and Cutts paper. And so I refer you to that paper as well as ours to see what we've done. But we're basing our description of four-wave mixing in the nonlinear Schrödinger equation system on a truncated system of a pump and two sidebands, described by a parametric representation in terms of amplitude and phase, or relative amplitude between the sidebands and relative phase between the sidebands. And we'll see this actually works with a more general description as shown in our paper, but the parametric representation is slightly simpler for the initial demonstration. When we plot the results of four-wave mixing using this parametric representation, these are the typical results we would obtain. On the bottom left, for two different initial conditions, we see a typical spatio-temporal representation where we'll see some energy exchange between the pump and sidebands leading to some complex spatio-temporal pattern. The corresponding evolution of relative intensity and phase for the two initial conditions are shown as the red and the blue curves respectively. In the middle, they're shown as line plots. On the right, they're shown as in a polar representation. The idea here is to, starting with only this data, to somehow reconstruct the generating parametric model. To test the feasibility of this approach, we generate 100 data sequences of amplitude and phase evolution, and we add 5% noise. A typical trajectory pair is shown on the left. We then configure the SINDI algorithm with a library of 32 different possible terms of all kinds that might describe the dynamics. This is where we input some guesswork, but it's fairly justified guesswork. We'd consider polynomial terms, trigonometric terms, and their combination. There's no bias associated with any of these. When we input the 100 data sequences into SINDI, it returns 100 models with different terms and associated coefficients. By plotting a histogram of the frequency of a particular number of right-hand side terms returned by the algorithm, we find there's a clear peak with only 6 terms. And since there's interest in physics to describe systems by the minimum number of terms, when we examine what these are and compute the associated coefficients, we find that the means of the return coefficients agree with what we expect from the ideal a priori knowledge within about an error of about 10 to the minus 3. Now this is remarkable, but they're very early results and we've really only scratched the surface. There's a lot more that we can do with this, and I think we're just starting. So these are the main conclusions. Feed-forward neural networks can be used to determine a predictive relationship between measured spectra and peak temporal intensity and modulation instability, noise like pulse generation, and the emergence of redshifted rogue solitons. Care needs to be taken to ensure that the spectra are measured with sufficient dynamic range if there are plans to do this with experimental data. In addition, feed-forward and recurrent neural networks have been shown to be able to replace direct integration of the nonlinear Schrödinger equation to determine evolution maps for solitron propagation and supercontinuum generation. And finally, although data-driven discovery is at a very early stage in nonlinear optics, our results studying four-wave mixing show its great potential to determine governing models based only on data. Thank you very much.